Good morning. My name is Ray Hesslein in the lower picture, and I'm speaking to you from Winnipeg, Manitoba, Canada. First, on behalf of Bob Hecky and myself, I would like to express how honored we feel to be given the Martin Award. 1995, when the paper Contributions of Benthic Algae to Lake Food Webs, as revealed by stable isotope analyses, was published, is quite some time ago. I have been retired from DFO, the Department of Fisheries and Oceans, and the Experimental Lakes area since 2009, so it was quite a surprise to be notified. However, I have to say it is gratifying for both of us to have colleagues and ASLO recognize that we made a significant and lasting contribution to our science. I hope we all in our careers and lives in general try to make a positive contribution to our world, and it is especially nice to have some of our efforts confirmed. I don't want to say too much about the paper itself. You can read it if you haven't, and it is 25-year-old science. There have been hundreds of papers on the use of stable isotopes for delineating food webs and defining food sources since its publication. Instrumentation for producing stable isotope data has advanced greatly since I and my lab mates operated manually loaded mass spectrometers and ourselves built interfaces for the automation that made the larger number of analyses required for this and other studies possible. Bob and I worked for DFO at the time, originally the Fisheries Research Board of Canada, but we didn't work in the same group. He was the leader of a group called Regional Limnology that in 1970s carried out a major study of southern Indian Lake in northern Manitoba on the effect of flooding for hydroelectric production, then worked on a project in the Mackenzie River Delta, and a study of the effect of size on lakes in northwest Ontario, before starting his long-term involvement in many studies on the large lakes in Africa. Through these studies, Bob's work has greatly enhanced the science required to manage fisheries, especially those of Indigenous peoples around the world. I worked with the Experimental Lakes area and had involvement in many types of whole lake experiments. My initial skills were in physics and chemistry, but at ELA I learned how to apply these skills to biological problems. I started work on stable isotopes, looking at sulfur in 1982 with application to acid rain related work, and we expanded our capabilities to be a significant isotope lab for C13 and N15 as we recognized the potential value of the technique. I also had experience with boundary layers because of work with colleagues at my alma mater, Lamont Doherty Earth Observatory, and follow-up work on boundary layers and benthic algae with Michael Turner at ELA. A lot of more recent work characterizing the turbulence of boundary layers with various micro techniques has been carried out since then. The concept of the model is simple. When one moves from the bulk of a water body, like a lake that is turbulent, to a solid wall like a rock, sediment, or even a macrophyte leaf, the velocities in the turbulent eddies must over some distance drop to zero. Because of the viscosity of water, a laminar layer remains. The thickness of that laminar layer depends primarily on the turbulent energy in the water. Higher turbulence means a thinner boundary. Surface roughness and temperature will also have some effects on the thickness of the boundary. If a dissolved constituent like CO2 is used up at the wall by photosynthesis, a gradient of its concentrations will be set up across the boundary layer. The gradient within the bulk of the lake will be small because of the higher turbulence. Virtually all of the gradient will be across the laminar boundary layer, inside of which molecular diffusion is the means of transport. The magnitude of the gradient will, of course, depend on the thickness of the layer, but also on the wall side demand of CO2. If the demand is very large, the concentration of the benthic algae will be zero. In this case, all of the CO2 crossing the layer will be used, and the isotopic fractionation associated with photosynthesis will not be expressed in the algae. The carbon in the algae will have the same isotopic ratio as the lake. If the photosynthetic uptake is slower, some back diffusion of the CO2 not fully used will occur, and some of the photosynthetic fractionation will be expressed. If the algal uptake is very slow, then the algae on the wall will look the same isotopically as the pelagic algae floating in the turbulent lake. The variation in the isotopic signature of the algae depends on two variables: the thickness of the boundary layer and the rate of CO2 uptake by the algae at the walls. Although the model is simple, variation in nature can produce a wide range of isotopic ratios in benthic algae in different systems. Turbulence varies with lake size and depth, as well as seasonally and with weather. Solar intensity driving the photosynthesis can vary with water clarity, depth, seasonality, and diurnally, as well as with minor location changes in the lake. Algal growth can also, of course, be affected by nutrients like phosphorus. Just a year after Bob and I published this paper, Bob and I, along with Michael Turner, were able to collaborate with Harvey Boetsma, also with Bob's African project, describing a relationship between isotope ratios and fish feeding in Lake Malawi. Lake Malawi has a large number of species that have evolved very specific algal feeding habits, even though they live in close proximity in the same lake. For instance, in species that lived within centimeters of one another, some fed only on the bottom of rocks where the sunlight was limited, and others only at the more productive top of the rocks. Because of the lower productivity in the shade, the isotopic fractionation was expressed to a greater degree. With the model in hand, we were able to make sense out of the range of isotope ratios and the ecology. It really was the perfect data set to show the power of the model and to corroborate the careful ecological observations that had been made in Lake Malawi. In Lake Michigan, another large lake with an important sport fishery, the understanding gained from our paper has helped sort out the changes in the food web due to the invasions of drysinids and the round goby, and to determine how they're influencing the stocked species. The gradient of isotopic ratios expressed across the benthic versus pelagic endpoints of Michigan is well expressed in this figure. Connecting higher organisms to their algal energy sources is much more logical with the use of the model. The impact is not simple. The invasion by drysinids has affected the photosynthetic productivity of both the pelagic and benthic zones, and differently at depth. Drysinids have also changed the conditions of turbulence at the boundary layer. The physics and the chemistry of the model give the tools to sort out those changes. In 2002, Daniel Schindler and Mark Shurel, and congratulations to Dan on the Hutchinson Award, in a review paper emphasized the importance of fish in participating in the coupling of benthic and pelagic food webs, and the importance that both sources of photosynthetic activity can have in supporting the upper trophic levels. They did point out, however, and I quote, that despite the extensive literature that has developed around the effect of fishes on lake food webs and ecosystem processes, very few studies have effectively linked benthic and pelagic habitats within a food web perspective of lakes. That was nearly 20 years ago, and papers like the Lake Michigan study of Turchak and Boetsma in 2015 show that has changed. Bob and I are very glad that our work continues to provide a basis for the interpretation in these studies. I have always believed that mechanistic models, properly integrated form the best basis of complete understanding of natural systems. It is challenging to produce mechanistic models that go from raw sources such as the atmosphere to complex organisms high in the trophic scheme. In this case, we were able to combine submodels from both the work of our own exceptional teams and work described in the literature to form a robust explanation of a complex relationship. Bob and I both were fortunate to work with exceptional teams. Every team member's science benefited from those relationships. The last 9 months of the pandemic, pandemic have been challenging for collaboration, but we are all fortunate to have modern tools to make it easier. Don't let the challenges stop you from talking to your colleagues. Thank you very much.